Test. All right, this video is for AP Calculus BC, and we're going to talk about trigonometric substitution. This is in addition to the trigonometric integral idea that we learned in the previous lesson, so make sure you're comfortable with that before you try this. That extends trigonometric integrals to a wide variety of other sorts of integrals, usually involving a radical in the integrating. So if straight u substitution doesn't work, then you can try this. I'll give you a quick example where you wouldn't want to use this, but where other techniques would work. Let's say that you had an integral where you had, let's say, x over the square root of 1 minus 2x squared dx. Right here, this is ready to go for a u substitution, right? If I decide to make u 1 minus 2x squared, the derivative of that would be negative 4x. du would be negative 4x dx, which means x dx would be negative 1/4 du. So I could just say, all right, this is just 1 over the square root of u, and this is negative 1/4 dx. And we can bring this 1/4 outside and solve this with shortcuts, right? So in this case, we don't need to do what we're going to learn today. So if you have a radical in a problem and you can see that u substitution works, always try u substitution first, because that's going to be much easier than the procedure that we learn next. Now, this next procedure, it is valuable. It's going to be for situations where you have, say, square root of 1 minus 2x squared dx, but you're missing the x, so you can't make u substitution work. This will be the procedure we do today. I would say when you talk to most students, they would put this one on the most difficult of the procedures, the integration procedure to use. But thankfully, this is the one that is encountered the least. I've yet to see it on an AP exam for AP Calculus, but it is useful, especially in engineering and physics kind of contexts. So it's definitely worth learning. Okay. So some integrals have a form in which a part of the integrand can be represented as a side of a right triangle. And then we can introduce an angle theta so that we can write expressions with the radical and other pieces using trig identities with this angle theta. So we're going to end up substituting in the original integral here, but we're going to change the integration from this variable, say x, to the variable theta, and we'll end up with a trig integral, something like this, right? Which at first doesn't look easier, but we can't really do u substitution here because the x we need is in the denominator, so we have to use a technique like this. The idea in general is, let's say we have this, we'll look at this one specifically. We have a radical with a square root of x squared minus 9. What we could do is draw a right triangle, and since we have a minus sign, I'm going to put this radical on one of the two legs. It actually doesn't matter which one. So we have the square root of x squared minus 9. Now, speaking of that, which leg we choose, there's different teachers that teach us in different ways, and different textbooks cover it differently, but I like to teach it in a way that has us memorize the least amount, because we already have enough to memorize in this class. So in the method I'm going to show you, you can choose either of the legs if you have a minus sign. We'll talk about later what you do if you have a plus sign. So I'm going to choose to put this square root of x squared minus 9 on this right leg here. And then I have to make these other two sides match so that the Pythagorean theorem would work here. Okay, so in this radical, we have a larger side and a smaller side. And the reason I know that this x is the larger side is that if this was the larger side, this would end up being a square root of a negative number, and we can't have that. So of the remaining two sides, the hypotenuse is the larger side. So if we made this x, and we made this the square root of this 9, which is 3, then the Pythagorean theorem would work. X squared is equal to this side, the square root of x squared minus 9 squared, plus 3 squared. And that means x squared would equal, when those outdo each other, x squared plus 9. I'm sorry, that's a minus 9. Minus 9. Let me back up there. Minus 9 squared plus 3 squared. x squared equals x squared minus 9 plus 9, x squared equals x squared, so that works. Right, so if you make the hypotenuse x the square root of this, and this side, the remaining leg, 3, the square root of this 9, this triangle represents the relationship between this radical x and 3. Okay, and then what you do is you pair up whichever side is a constant with the other two sides, so 3 with x and 3 with the radical, and you find a trig function to represent that ratio. Right? So 3 with x, we have the adjacent side to this angle and the hypotenuse, and adjacent over hypotenuse is cosine. So the cosine of this angle theta is the adjacent side 3 over the hypotenuse x. And that means that if I multiply both sides by x and divide by cosine, x is 3 over cosine, and therefore x is 3 times secant. Right, so that gives us a way to change the x into the variable angle theta. Right, to get the other relation that we need, we're going to pair the constant side with the radical. So that is opposite and adjacent, which is tangent. So the tangent of this angle is the opposite side, square root of x squared minus 9 over the adjacent side 3. When we multiply, that means that the radical, the square root of x squared minus 9, is equal to 3 times tangent. So by pairing the constant with each of the other two sides, we can get an expression for x and an expression for the radical in terms of this angle. Now, if I want to substitute back in here, that means that I can substitute this x squared minus 9 with this, let me just actually show it over here. So I'm going to take this integral. Change colors here, I'll use blue. So we have the square root of x squared minus 9 over x dx. Right, this radical, I'm going to substitute this 3 tangent of theta in for that. And this for this x in the denominator, I'm going to put 3 secant of theta. Right, but for the dx, I need to take this part of the toolkit, this x is equal to sine or secant of theta, and take the derivative. So the derivative of dx with respect to theta is 3 times the derivative of secant, which is secant times tangent, which means that this dx gets replaced with 3 secant theta tangent theta d theta, which at first looks pretty bad, like it's going the wrong direction, getting more difficult. But we got some cancellation that happens here. These secants cancel, these 3's cancel, and you're just left with 3 times tangent squared of theta d theta. And that, we've converted this from a regular integral with a radical into a trigonometric integral that we learned how to deal with in the last section. So with the power for tangent squared, we can take that tangent squared, substitute secant squared minus 1 in, split that into 2 integrals. The integral of secant squared is tangent, so this becomes 3 times tangent, and the integral of 3 times 1 is just 3 times theta plus c. And then this is the answer in terms of this triangle. So now we want to use the triangle again to substitute back to the original variable x. So to do that, this tangent is the opposite over the adjacent side, so that gets replaced with square root of, we just take this over here, we have 3 times tangent of theta plus 3 times theta plus c. So for this tangent, I'm going to replace this with the tangent of that angle is the opposite side over the adjacent side. And for this theta, we can take the expression that we had up here, which was let's see, well, there's a couple ways we can go here. So we've got 2 expressions here. We've got, let me show this over here. I'm going to change colors to get too much red on the screen here. We have that x is 3 secant theta. And we also have that the radical square root of x squared minus 9 is equal to tangent of theta. So we can solve either of these 2 things for theta and plug it in here. So there's 2 actually correct answers. You could say if secant of theta is x over 3, we could say theta is the inverse secant, or arc secant, of x over 3. And we could put arc secant of x over 3 in there and add our c and we'd be done. That's valid. You can also make those cancel. Or you could also say this is the square root of x squared minus 9 plus 3. And you could solve this one for theta by saying that if the tangent is that, then if you take the inverse tangent of this, theta could also be the inverse tangent of the square root of x squared minus 9. Right, so you could also, what is that, times 3, is that right? Yes, there's a 3 here, divided by 3. So we could also say that this is the arctangent of the square root of x squared minus 9 over 3 plus c. And either of those answers are correct. Right? The goal is to come up with an antiderivative of this. And either of these, if you take the derivative, will produce this. All right, so that's the idea behind trigonometric substitution. It is admittedly pretty complicated. But the idea is if there's no other way to evaluate this, other than like Math 9 if you have a definite integral, then at least you can get an expression for the answer here. It involves making a triangle where you place the square root, the radical part, as either a leg or the hypotenuse in some cases, on the side, figure out the other two sides, pair up the constant with both of the other sides to form two trig ratios, solve one of them for x and one for the radical. The one that's the x you take the derivative of to get the dx, and then you substitute x, dx, and the radical back into the original integral to get a trig integral. And then you do whatever you need to do to solve that trig integral, and then you use the triangle to resubstitute the theta back in terms of the original variable. That is a lot of work. All right, so we'll look at some specific examples, and you can always try pausing these. So did we just do that one? Yeah, we just did that one, so I don't need to do that one over again. But just the reason why that we decided to put the radical here on the leg here is because we had a minus sign. And that means that one of these sides is going to be the u, but this has to be larger than this side here, so it must be the hypotenuse. Okay, and this was the whole thing worked out. Let's try another one. What did we have this one? We had an integral of x cubed over the square root of 16 minus x squared. We would build a triangle on that. The idea is we're going to build a triangle where this radical will be, since there's a minus sign, one of the sides. I'm thinking of this 16 as 4 squared and this x squared as x being squared. That means this 4 here is going to be the hypotenuse of the triangle because it's got to be the large side. Right? I could make a triangle here where this is theta. If I made this side 16 minus x squared, this side would have to be 4 and that would be x. Or these two things could be swapped. It really doesn't matter which one you do. You can still get an answer. Okay, so let's go ahead and do the entire procedure here. I like to use the right-hand side, so we'll do that. Let's see, the right sides. Okay, so I'm going to make a triangle to match this radical situation. I've got a triangle. I'll put an angle theta. I'll put the square root here because there's a minus. I'll put it on a leg. I'm going to put it on this side over here. But that means this would have to be 4, so that 4 squared produces that, and this would have to be x. Let's just see. X squared, so this would be this side, just to double check, x squared plus 4 squared equals, x squared plus square root of 16 minus x squared has to equal 4 squared. Is that true? X squared plus 16 minus x squared equals 16. Sure enough, that's true. So we've got this right. You can always see if this is set up right by checking it with Pythagorean. All right, so here we go. What we're going to do is pair each of the sides with the constant. So if I pair this with the constant, that is adjacent and hypotenuse. That means the cosine of the angle theta is the adjacent over the hypotenuse. And if I pair this with the other side, that is hypotenuse and opposite, so that is sine. Sine is the opposite side over the hypotenuse. We'll solve both of these for the variables. So that means x here is 4 times cosine theta, and the radical is equal to 4 times sine theta. And we're also going to need a dx, so we can get that by taking the derivative. Dx d theta here is negative 4 cosine of theta, so dx is negative 4 sine of theta d theta. Okay, then what we're going to do is substitute all this back into the original integral to change its letter from x to theta. So first, x cubed. Well, x is 4 cosine, so I'm going to put 4 cosine theta in there and cube that. This radical gets replaced with 4 sine theta. And the dx gets replaced with a negative 4 times the sine theta d theta. Okay, so what do we got here? We've got 4 times 4 is 16 times 4 is 64. 64 cosine cubed of theta. This 4 and this 4 will cancel, and that sign cancels, just leaving a negative 1. So, let me go back here. 64 cosine theta. And then we've got that 4 cancels, the sign cancels, negative. There we go. So after all of that, we have, that's a cube. We have 64 cosine cubed, right? We have three 4s multiplied and 3 cosines multiplied. The 4s canceled, everything but the negative. All right, so now we've converted this into a trig integral. So that means we're going to do what we learned in the last lesson. We're going to say, if I were to decide to write everything in terms of sine, let's say, then that means the derivative would be cosine. So du would be cosine theta d theta, which means I'm going to reserve 1 cosine on the side. So I'm going to put a negative 64 out there. We'll bring the 64 outside. We're going to take a cosine squared here, reserve a cosine for the du, and then that cosine squared is going to be replaced with 1 minus sine squared cosine theta, which means I can split this into negative 64 just times the cosine theta d theta, minus is plus 64 sine squared theta cosine theta d theta. Here we can do just an integral, antiderivative shortcut to get that sine. But for this one, we're going to do a u substitution with this u. This is now du. We've got negative 64 sine theta plus 64 times u cubed over 3 plus the c. And let me write the result here. So now we've got that this is negative 64 times sine of theta plus 64 over 3 times, this is now sine cubed of theta. Okay, now we're not done yet because this is still in terms of the theta. So now we have to go back to the x. So to go back to the x, what we'll do is use the fact that x's get replaced with 4 cosine thetas. Actually, we'll use the triangle up here. So I need to replace that sine. So what is sine equal to? Well, up here we said sine of theta is the square root of this radical. Square root of 16 minus x squared over 4, which means I can replace each of these signs with that to go back to the original x. So I have 64. This sine of theta becomes square root of 16 minus x squared. Square root of 16 minus x squared over 4 plus 64 over 3, and then that square root of 16 minus x squared over 4 but cubed. Tack on our plus c and we're done. This is the final answer here. So that's how trigonometric substitution works. You use a triangle to convert everything into this angle theta. Substitute back in the original integral, do a trig integral, and then use the triangle to convert back to the original x. It is not trivial though. Just to show you that you could have used either side, let me show you one more example of this. I'm just going to erase that result here. But we're going to set up the triangle the other way, it will give a different looking answer, but which is also correct. I'll go a little faster here. What if we decided to put the radical on the other side? We still have an angle theta here. What if I decided to make this side the 16 minus x squared? This would still be 4, this would be x. And then when I pair up each of these things, I would have that this pair is cosine of theta is the adjacent side over the hypotenuse, and this side would be sine of theta is the opposite side over the hypotenuse, which means that x would be 4 sine theta. The radical would be 4 cosine theta. We would take the derivative here and get dx is 4 cosine theta d theta, and then substitute in the integral. So to convert to a trig integral, this is equal to the x cubed in this case would be 4 sine theta cubed over the radical is being replaced with 4 cosine. The dx is 4 cosine theta d theta. These would cancel. We would have the same 64, but this time sine cubed theta d theta. And then to enable a u substitution, we could do u is cosine, so that the derivative is negative sine theta d theta. So I know I can reserve one sine. And that makes this sine squared theta with our sine over there, d theta. That means that we could replace the sine squared of theta with 1 minus cosine squared theta. We could distribute that and get 64 times the integral of sine minus 64 times the integral of cosine squared with the sine, and then do the u substitution where needed. So this is just the negative cosine. And we have negative 64. This would be the integral of u squared, but this is actually negative du. So this is going to become a positive there in du, which means this is 64 over 3u cubed. We have a negative 64 cosine plus the c. And then I'm going to substitute, I'll go back to the other color here. So I've got a negative 64 cosine of theta plus 64 over 3, and then cosine is near here, so it would be cosine cubed theta plus c. Then to get rid of these, the cosines, if I go, I use this to substitute out the cosines, I would get negative 64. I'm substituting square root of 16 minus x squared over 4 in for that, plus 64 over 3 times the square root of 16 minus x squared over 4 for this cubed, plus a c. Okay. And that should be either identical or similar in form to the other one. I guess I have erased it. So sometimes this will look a little different, but as long as you go through the process correctly, it is a valid antiderivative. So it doesn't really matter which leg you put this on. Now some teachers do teach that there's a specified preferred leg. In the case of sine and cosine, it doesn't really matter that much, but when you have secants and tangents, sometimes you end up working with secants in one form and cosecants in the other form. So some people are more comfortable with one or the other, but it will work and give a valid expression regardless of which leg you put that on. So far, we've seen radicals with a minus sign inside. What happens if you have a radical with a plus sign? Okay, the difference there is just that the radical has to become the hypotenuse because it's going to be longer than either of the two sides. The rest of the procedure is the same. So let's go through this, and if you want to try it on your own, give that a shot. I would draw a triangle, put an angle, and then I'm going to put the radical on the hypotenuse this side, which again means I can choose either side for the legs here, and I'll just do one of the two. Let's put the x over here, and then this 2 would be 2 squared, so that would be 2 here. Again, you could put the x here and the constant here. I find it's a little easier usually to put the variable on the right-hand side and the radical on the right-hand side, so I tend to do that. All right, so we're going to pair the constant with each of the other sides. So that means we'll pair this one and get that's opposite and adjacent, so that is tangent. Tangent of theta is opposite over adjacent, which means we can solve this for x and get 2 tangent of theta. Yes, okay. And then we can also pair this side and with a constant, the radical. That is adjacent and hypotenuse. So that is cosine of theta is the adjacent side of the hypotenuse, which means if I solve for the hypotenuse, I have the hypotenuse is 2 over cosine theta or 2 secant of theta. So we have things that can transform into each other, tangents and secants. This side is the one I'm going to use to take the derivative to get the dx. The derivative of tangent is secant squared. And now I can substitute in the original integral. All right, so this is equal to the x cubed, if the x is 2 tangent, so 2 tangent of theta being cubed. That radical gets replaced with 2 secant. And then the dx gets replaced with 2 secant squared. Okay, let's simplify this a little bit. We have 2 cubed, which is 8 times 2 is 16 times 2 is 32, right? So 32, I'll bring that out. We have a tangent cubed and a secant cubed. Okay, so thinking about this, right, it'd be nice if we could get even powers for tangents and secants, because both of those could be converted to the other form. I have an odd for both, but if I decide to make my u secant, then that means that the derivative is going to be secant times tangent, which means I have to reserve one of each, which will make both of those even powers, which is the preferred situation. So let's take this down to a tangent squared and a secant squared, so I can get a secant and a tangent on the side to reserve for my du. And then, since that's the derivative for the u, with a secant, we're going to have to convert everything to secant, so I'm going to need to convert the tangents. So on the side, I'm thinking, okay, I've got sine squared plus cosine squared is 1. If I want tangents, I can divide everything by cosine squared. This is the Pythagorean identity. So tangent squared plus 1 is secant squared. So tangent squareds can be replaced with secant squareds minus 1s. So that means this is 32 times the integral of secant squared minus 1 times another secant squared times our secant tangent that we're reserving for use for the u substitution. And then I can distribute this in here, so I've got 2 integrals. 32, integral of secant squared times secant squared is secant to the 4th with the secant tangent. And I've got minus 32 times just the integral of secant squared with the secant tangent. And then I can do the u substitution, so that's 32 integral of u to the 4th, and this whole thing is the du, minus 32 integral of u squared du, which means that's 32 over 5 u to the 5th, so u, minus 32 over 3 u cubed plus 3. I'm going to change colors and write the result over here. So we have 32 over 5 times u, which is secant, to the 5th power, and then minus 32 over 3 times secant cubed plus our c. Now, to take those back to the original x, I'm going to have to somehow use this. But right here, I've got that 2 secant of theta is that. So that means that secant of theta is just the radical x squared plus 4 over 2. So I can replace each of those with the radical x squared plus 4 over 2. And then that one has to be to the 5th power. 32 over 3 times the radical x squared plus 4 over 2 to the 3rd power plus c, and that is the answer. And you'll get slightly different forms throughout here with cosecants and cotangents if you happen to put the x here and the 2 here, but that would work. You could still use that as well. I know this video is getting a little long, but there's only one more example here. You can skip this if you already have enough to be able to do your homework problems to practice, but we'll do one more. Okay, this introduces a little bit of a snag here with the x squared. This is not just x squared, now it's x to the 6th. So first of all, that radical. The square root of x to the 6th minus 4 is the same as x cubed squared minus 2 squared. Would you agree with that? So when I make my triangle, let's see, I've got a minus sign, so the radical is going to go on one of the sides. That means the hypotenuse is x cubed, because x cubed squared will produce that, and then this will be 2. So really the only twist is that we're going to have an x cubed for the hypotenuse. Okay, we always pair up the constant with each side. So the simplest pairing here is adjacent and hypotenuse. So that's going to be cosine of the angle is the adjacent over the hypotenuse, which means that x cubed is equal to 2 over cosine or 2 sine, 2 secant, right? And that does mean I'm going to have to solve for x. So I'm going to have to take that and undo that by raising both sides to the 1/3 power. All right, let's pair this with constant with the other side here. That is tangent. Tangent is opposite over adjacent, so x to the 6th minus 4 over 2. And then I'll solve this for the radical. So the radical is x to the 6th minus 4 is equal to 2 tangent theta. And then I do need the derivative here, so I can replace the dx. So we'll take the derivative here. Dx d theta is, by extended power rule, 1/3 2 secant theta to the negative 2/3 power when I subtract 1, because we're doing derivative here. And then the derivative of secant is secant times tangent, the chain rule. So the dx is that times d theta. All right, I think we're ready to do the substitution. Hopefully there'll be a lot of cancellation. Okay, the radical gets replaced with 2 tangent. 2 times tangent theta. The x gets replaced with 2 secant of theta to the 1/3 power. Right? Okay, and then we have a dx, which is 1/3 2 secant theta to the negative 2/3 power, secant theta tangent theta d theta. Wow, lots going on. But there's going to be some cancellation. Let's look at the constants first. We've got, let's see, a 2 from here. We have a 2 to the 1/3 power here. We have a 1/3. And then we have a 2 to the negative 2/3 power there. Right? So how could these things combine? That's going to be a 2 and a 1/3. So, and then we have 2 to the negative 2/3. 2 to the negative 2/3 divided by 2 to the positive 1/3, which is the same as 2 to the negative 2/3 minus a 1/3, which is going to be 2 to the negative 1. Right? So 2/3 times 2 to the negative 1, which is 2/3 times 1 over 2, which is just 1/3. So after all of that, we just get 1/3 as the constant. Okay, so I'm going to bring that on the outside. Okay, then there's going to be some cancellations as well here. So what do we have left? We have a tangent and a tangent, so that is a tangent squared. We have a secant, and then we have this. We have a secant to the negative 2/3 power, and on the bottom we have a secant to the 1/3 power, which means if I raise this to the top, this is secant to the negative 1/3 power, which means this is equal to 1/3 integral tangent squared. Now we have a secant times a secant to the negative 1, which just means it's 1 over secant. So the secants totally cancel out, and you end up with 1/3 integral tangent squared theta d theta. Okay, so how do we handle tangent squared? Well, what if we just try to go to secant? Because, yeah, let's try integrating here. I'm going to change colors a little bit. A lot of some color on the screen. So what if I said, I know that sine squared plus cosine squared is 1, so when I divide everything through by sine squared, I get, actually I need a tangent, so let's divide everything through by tangent squared, or cosine squared. Cosine squared, that's going to give you tangent squared plus 1 is secant squared. So tangent squareds can be replaced with secant squares minus 1. So this is 1/3 integral secant squared minus 1 d theta, which means I can split that into two integrals. An integral of secant squared, and then minus just an integral of 1/3. Because we have a shortcut, right? Derivative of tangent secant squared, so the integral of secant squared is tangent. And this is minus 1/3 times theta. All right, so after all that, I'm going to go back up here. I'm going to erase part of this. All this here. Okay. Let's look at the results. Okay, so this original integral is equal to 1/3 tangent of theta minus 1/3 theta plus an integrating constant. So we've got to replace these. Tangent of theta is radical x to the 6 minus 4/2. And for this theta, we can either take either of these sides and figure out what theta is. Maybe we take this one. This is a little simpler. No, maybe we don't, because of all that. Let's use this one. Use this one because tangent of theta is the square root of x squared minus 4/2. So that means the angle is if I just take the arctangent. So yeah, I'm going to do that. This is a 1/3 arctangent of the square root of x to the 6 minus 4/2 plus c. Good. Now we have an expression for an antiderivative, and it's converted back to its original variable. Okay, you could get slightly different forms here depending on if you wanted to solve for this one. You would have something in terms of arc secant here. That can be done. But I think this is probably the one you would see the most. As I said, I think at the beginning, this trigonometric substitution is the least commonly encountered. I've not seen it yet on any AP exams. I don't think it will ever be on an AP exam. However, it is part of the course to know it. And even though it is the most difficult one, most people would say, you can do this as long as you practice.